All right, so the last session in this review is covariance and correlation coefficient, okay? So now we know from our previous tutorial that if we want to measure the variation of a random variable, we make use of the variance or the standard deviation, okay? So in the case of a bivariate distribution, how do we quantify the measure of dispersion or variation? This is done by using the covariance or correlation coefficient, okay? So the covariance between two random variables, x and y, is a measure of the nature of the association between the two random variables, okay? In other words, we can say that the covariance between x and y describes the variation between the two random variables. Now, the sign of the covariance indicates whether the relationship between the two random variables is going to be positive or negative. Covariance only describes the linear relationship between two random variables. Therefore, if a covariance between x and y is 0, x and y may have a nonlinear relationship, which means that they are not necessarily independent. Now, take note of this. When x and y, or when the two random variables are statistically independent, it can be shown that the covariance is 0. However, the converse or the reverse is not generally true. That is to say that two random variables may have 0 covariance and still not be statistically independent. Okay, so take note of that. Now let's take a look at this definition. Let x and y be random variables with means mu of x and mu of y respectively. The covariance between x and y, denoted by sigma index as pi, which can also be expressed in this form, is given by equation 22. Okay. Now, if you recall from our previous tutorial on expectation of joint distribution showing 2, equation 15, we saw this, okay, and we said this is equal to covariance. So this is similar to expectation of x, and this is similar to expectation of y, okay? So when your random variables x and y are discrete, you can use this to obtain the covariance. And if x and y are continuous, you can use this as an expression to obtain the covariance, okay, between the two random variables. All right, let's take a look at the properties of covariance. For any random variables x and y and z, and any constant a and b, the covariance of x and y is similar to covariance of y and x, and also covariance of x and x is equal to variance of x. Okay, you guys have to take note of this because it will be relevant in our subsequent tutorials. Okay, also the covariance of a constant and random variable will always be 0, and the covariance of x, y plus z can be expressed in this form. So we take the covariance of xy plus covariance of x and z. Okay, now the covariance of ax and by can be expressed this form. You just have to pull the constant out so that you can take the covariance of random variables. And also the covariance of xy will be 0 if x and y are independent. Okay. All right. So let's take a look at this framework. For any random variables x and y, the variance of x plus y can be expressed in this form. Okay. And also the variance of ax plus by can also be expressed in this form. Now the variance of x minus y can also be expressed in this form. And the variance of ax minus by can also be expressed in this form. Okay. Now for independent random variables x and y, the variance of x plus y will be in this form. So and the variance of x minus y was be in this form. Okay. All right. So let's take a look at an example. Let x and y be discrete random variables with means equal to leave a mean for x and leave a mean for y, okay, with joint P and F given below. So we want to find the covariance between these two random variables x and y, okay. So let's take a look at the solution. So we are given the mean for x to be that and the mean for y to be that, okay. So, you know, covariance, we are supposed to obtain this expectation of xy, which can be expressed in this form. Okay. So, first of all, you know that the possible values for y is from 1 to 2, and the possible values for x is from 1 to 3. Okay. So, we can decide to start with x, want to sum over the region of x, so we input the values for x, right? So when x is 1, you obtain this. When x is 2, you obtain this. And when x is 3, you obtain this, okay? So once you input 1 here, you obtain this. Once you input 2 here, I have put this constant out, 1 out of 20, 1 out of 21 out. So I'm just dealing with this minus, okay? That's what we have here. All right, so now I want to sum over the region of y, okay? So when y is 1, you obtain this. So you input 1 here, you obtain this. You input another 1 here, you obtain this. You input another 1 here, you obtain this, okay? So the second probability value for y is 2. So when y is 2, you obtain this, okay? So you input 2 here, you obtain this. You input 2 here, you obtain this. You input 2 here, you obtain this, okay? So we can now use our calculator to compute this, okay? So once you try to sum all this, multiply this, and sum, you obtain this. So if you use a calculator to compute this, you obtain that, okay? Very quite simple. We know covariance is given by this expression, so we have already obtained this, and we're given this too. So once you try to input this, we obtain this, and you can use a calculator to compute this to obtain that, okay? Very quite simple. All right, let's take another example. The random vector xy has PDF shown below, and also we have the marginal PDF shown below. So we have the marginal PDF of x and marginal PDF of y, okay? We want to find the covariance of x and y. So how do we do this? So we first have to find the mean of x, and also we have to find the mean of y, okay? Then we can also find the expectation of xy. So this is the expression for the mean of x, okay? So once you use your calculator to compute this, you can obtain this. And I assume you know how to do this because you have already seen this from a previous tutorial, okay? So to obtain the mean of y, you can use this, okay? And once you calculate to compute this, you obtain this. So now I want to find the expectation of xy, which can be expressed in this form, okay? You can also express it in this form. So here we have to integrate first with respect to x before with respect to y, or you can decide to integrate with respect to y before with respect to x, okay? If we look at the possible values, I'm sure. So we can see that x and y range or lies within the interval 0 and 1, but x is less than y. So if y is from 0 to 1, then x can pick values from 0 to 1, okay? Or if you decide to pick x from 0 to 1, then we can pick y from x. The range for y will be from x to 1, okay? So that's basically what we have in here. That's basically what we have here. You see that this one, we go by this. So I'm going to go by this approach. So once I multiply through by this variable function, I'm going to obtain this. So I'm going to integrate first with respect to x, and this is the range for x. So you integrate, you obtain this, you input the values, you obtain that, okay? So we are now going to integrate with respect to y and obtain this. You try to input the values, you obtain that, okay? All right, so now our covariance is given by this expression. We have already obtained this to be that. We have the mean to be that, and once you try to use a calculator to compute this, you obtain that, okay? Very quite simple. All right, so now to correlation coefficient, okay? So why do we need correlation coefficient? The correlation coefficient of x and y is a dimensionless quantity that measures the linear relationship between the random variables x and y in different units, okay? What this means here is that we know that the covariance is not scale-free. Because it is not scaleless or it's not scale-free, the magnitude of the covariance always depends on the unit used to measure both random variables x and y. Okay, this is what I mean. So let's assume x is in centimeters and y is in meters. The covariance that we have here will have the unit attached to it. So here we have centimeters and meters, okay? So this follows that the magnitude of this covariance does not indicate anything regarding the strength of the relationship between the random variables, okay? So in order to make this scaleless or scale-free so that we can have the actual strength between the random variables, we try to make use of the correlation coefficient, okay? So the correlation coefficient will standardize the covariance by the standard deviation of each variable, okay? And once this is done, we can then determine the actual strength between the two random variables, okay? So let's take a look at this definition. Let x and y be random variables with means mu of x and mu of y respectively. The correlation coefficient denoted by rho index xy between x and y is given by equation 24, okay? So the correlation coefficient is denoted by this, and we can express it in this form. So this is going to be our covariance, right? And this is standard deviation, divided by standard deviation, and this is to standardize the covariance so that we can have a dimensionless quantity, okay? You can also express it in this form, and always the correlation coefficient will always range from -1 to 1, okay? All right, so now let's take a look at this example. Using the information from example 14, we want to find the correlation coefficient of x and y, okay? So let me show you example 14. So this example 14, once you try to input the values when x is 1 and y is 1, you obtain 2 out of 21. And that's basically what we have here. Okay, so when x is 1 and y is 2, you obtain this, okay? And you can also get the margin for x and margin for y, okay? It's very quite simple. All right, so now we want to find the correlation coefficient of x and y, okay? So we are given this, you already know this from example 14, you already know this, and also you know the covariance, okay? So now I want to find the mean, I want to find the standard deviation or the variance of x and the variance for y, or standard deviation for y. So let's start with how do you obtain the variance or the standard deviation for x? We have to first of all get um, the second moment about the origin, okay? And we can obtain it in this form. So once we try to input this, we obtain this. How do we get this? So let me show the table again. So we know there's the marginal for x, so we try to square this and multiply by the marginal PMF of x, square this, multiply by that, square this, multiply by this, okay? So for y, we're also going to square this, multiply by the PMF of y, square this, and multiply by the PMF, okay? That's basically what we're trying to do. So once we get a second moment about the origin for x, we can then get the variance for x, okay? So we have it in this expression, we already know this. So we try to input the values and we get this, okay? And we know the variance of x is going to be the square root of the standard deviation of x is going to be the square root of the variance. So once you try to input this, you get this, okay? All right, so now we can do the same for y. We now want to obtain the second moment about the origin for y. So this is going to look like, okay, once you try to compute this, you obtain that. So then the variance of y can be obtained in this form. So you input the values and you obtain this, okay? So therefore the standard deviation of y can be obtained this form, okay? So therefore the correlation coefficient of x and y, I use this expression. So once we try to input the values, we get this, okay? And now we can see that we have an inverse relationship between the two variables, okay? All right. So now let's take a look at another example. So using the information from example 15, we want to find the correlation coefficient between x and y. So we have the joint PDF and also have the marginal PDF of x and y, okay? All right, so first of all, we know we have the mean, we have the mean for x, we have the mean for y, those are the covariance. So we are supposed to get the variance for x as well as the variance for y, okay? So let's start with s. Let's get a second element about the origin for x, which can be obtained in this form. So you can actually express this also in this form. Then once you use your calculator to compute this, also obtain this, okay? Then you can get a variance for x, which can be expressed in this form. So you try to input the value. So this is the expectation of h squared, which is 103, minus the mean squared, which is the mean for x, okay? So you input this, you obtain that. Then you can also get expectation or a second moment about the origin for y, this one. which can also be expressed in this form. And once you use your calculator to compute this, you obtain this. And you can then the variance for y, which can be expressed in this form. So we know expectation of y squared is this, and this is the mean for y, okay, 4 out of 5. So you input the values, you obtain this, okay. So therefore, the correlation coefficient of x and y can be expressed based on this. So we know our covariance, we have our variance, so square root of variance standard relation. So you obtain this, and once you use your calculator to compute this, you obtain this, okay. This is very quite simple. All right, so this is a trial question. I will leave the solution in the description of this video, so you can check it out, okay. So please, if you find value into this tutorial, don't forget to subscribe if you have not. And thank you for watching.